As with anything dealing with rotational motion, angular momentum can be tricky. Kinetic energy is not conserved. Even though angular momentum stays the same, kinetic energy absolutely changes. You felt that when you're spinning in the chair and you bring your arms in, your angular velocity is speeding up. If your angular velocity is speeding up, there's a chance that your velocity is speeding up also. Right? When the rod rotates slowly, its rotational inertia is I, angular speed is omega. When the weights move in, the rotational inertia is divided by 4, so the angular speed must be multiplied by 4 to keep the same momentum. The initial kinetic energy of the rod is slow, K equals 1/2 I omega squared. Final kinetic energy is fast, 1/4 of I times 4 times the omega. So it becomes 2 times omega squared, rather than half of omega squared. The omega is squared, the I is not, so multiplying omega by 4 is not canceled by dividing I by 4. If an object's moment of inertia decreases and angular velocity increases, but angular momentum is conserved, then the kinetic energy would then increase. Likewise, when your moment of inertia increases and angular momentum decreases, kinetic energy will decrease. An object in uniform circular motion has angular momentum that is conserved. Planets orbiting. Mario watching a ball. There's a force acting on the object, whatever force provides that net centripetal force. If it's a planet orbiting, it would be gravity. If it's Mario twirling a ball on a string, then it's the tension in that string. But that centripetal net force is directed towards the center of the circle. Remember, centripetal means center seeking. So the centripetal net force does not produce torque. No torque means no change in angular momentum. An object traveling in a straight path with a constant speed has conserved angular momentum. If an object travels in a straight line with a constant speed, the forces on the object balance out. Because it's a constant speed, right? That's our equilibrium. That automatically means that any torques produced by those forces also balance, because all of the forces act at the same point. No net torque means no change in angular momentum. Don't forget that a translating object moving in a straight path has angular momentum that is easily calculated using L equals mvr. That's perpendicular. So this equation here is kind of like the bridge equation. It's bringing us from linear momentum to rotational momentum. It's taking a linear moving object and applying a circular thing. It's the same idea as using omega equals V over R. Here we're multiplying the perpendicular distance to the momentum. You just have to realize that that distance has to be perpendicular to the velocity. The distance between the axis point and the line which the object travels. Because V and R are constant, L will be constant.